Okay, this is CET236 and we're in spring 2022 and I'm looking at homework set 2, which is about Kershaw's voltage law, Kershaw's current law, voltage dividers and current dividers. Okay, so let's have a look at problem 1. So I might need to reduce the zoom on my screen so we can see what's happening. There we go. Right, so here we've got a voltage source and 3 resistors. The values of the resistors are given in the table below, as is the voltage source. And the question's asking we're not given the voltage source, we're given the output voltage, the voltage across R2. And the question is, what is the supply voltage, Vs? So let's have a think about how that works. All right, and we'll take a screenshot of that and come in here and put that it's probably a bit big. There we go. Okay, so what do we know about this circuit? Well, we know V equals IR, and we could redraw this circuit just as a Vs and an REQ, single equivalent resistance. The thing to check is what relationship R1, R2 and R3 have to each other. And the relationship they have is series, right? R1 and R2 share node A uniquely, and R2 and R3 share node B uniquely. So we can find the single equivalent resistance just by summing up the resistor values, right? R1, R2 and R3. So that's going to be 10 plus 4 plus 8, which is 22 ohms. Now the other thing we know is we know that R2 is 4 ohms and the voltage across R2 is 4 volts. So that means we've got 4 equals I times 4, right, which implies that the current is equal to 1 amp. Okay, now the current that's flows, I'm going to say this way, this is an active source, so I can say that the current is flowing out of the positive side. And now the current doesn't have anywhere else to go, right? So all of the current is flowing through the 3 resistors. So again, I can then use V equals IR, but this time I know my current is 1, but now the resistance is REQ, right, which is 22 ohms. Oops, 22 volts, right? So 1 amp times 22 ohms gives me my 22 volts. And I think that's correct. Let me just submit my answers just to check that it's correct. It looks good. And I'll go to the next problem. Anybody has any questions, feel free to just speak up, and I'm happy to answer them at any stage. So where are we? Back here, problem 2. Okay. Now we have a current divider question by the looks of things. So we're after finding I2 and R2, given what we know about everything else. We know IS, so let's take a picture of that. Okay, so the thing we're after, let me just go back to the question, we're after I2 and R2. Given what we know about everything else. So one thing we can figure out is this node up here, right? Let's go with a green color. This node up here, right, has IS flowing into it and I1 and I2 and I3 flowing out. So one way to use Kirchhoff's current law is to say that the currents flowing into the node equal the currents flowing out of the node, right? So in this case we could say that IS equals I1 plus I2 plus I3. Okay, so that means we know IS is 20 amps and we know I1 is 4. We don't know I2, but we know I3 is 12 amps. So here we've got 16 amps and here we've got 20, so that implies to me that I2 is also equal to 4 amps. So then we've got to figure out what R2 is. And how do we do that? Well, there's a couple of ways we could do it. One way is to say VR2 is equal to IR2 or I2 times R2, right? But we know because R1, R2 and R3 are all in parallel, right? Remember, parallel means that they're connected between the same two nodes, right? And this let me get there's only two nodes in this circuit, right? So all three resistors are connected between the same two nodes. So that means the voltages across them are equal, right? So VR1 equals VR2 equals VR3. So even though we don't know VR2, we can figure out what VR1 is, and that's going to be the same. So VR1 is I1 R1, and that equal to I2 R2. So I1 is 4 amps, R1 is 6 ohms, right? And then I2 is 4 amps, and R2 is unknown. So that means that R2 equals 6 ohms. Right, and again, WebWork doesn't expect you to write the capital Greek letter omega, so just use OHM as the units here. Okay, let's have a look at problem 3. Ooh, this is a bit of a tricky one. It's relatively straightforward once you... Let's try and grab the problem number as well. I should have done that before. Okay, here's problem 3, and we're asked to find the equivalent resistance of this rather interesting circuit, right? And the circuit is interesting because of the way the resistors are drawn more than anything else. What you've got to do though is you've got to try and remove the confusion and just draw out where the nodes are, right? Where the areas of constant voltage are. So this is one node, and then the other node, funnily enough, starts down at B, and goes up here and here, okay, so there are only 2 nodes in this circuit, A node and B node. And I think you'll find, if you trace through R1, R2, R3 and R4, that one side of the resistor is on the blue node, node A, and one side of the resistor is on the green node, node B. Right? So all 3 resistors are in parallel. So RAB is equal to 1 on R1 plus 1 on R2 plus 1 on R3 plus 1 on R4, right, which is equal to 1 on 60 plus 1 on 60 plus what's that, 2 on 60 plus 4 on 60. which is 1 on, I think that is 8 on 60, and that is going to give us 60 on 8 ohms, which is equal to 7.5 ohms. Oh, and that whole thing that I just drew is not going to stay. Let's just write that out again. Oh, even the drawings I did. Let's do that again. Sorry about this. So our B node is all the way down here. And our A node is everything on the top side. And everything disappeared. That's a little annoying, right? And as I said, RAB equals 1 on R1 plus 1 on R2 plus 1 on R3 plus 1 on R4, because all of those resistors are in parallel. So just quickly, which is 7.5 ohms, and it's died again. And let's just check that I still have the right answer. I think it's still right. Yep. So let's go to problem 4. So this is something I haven't talked about. I've talked about resistance. What I haven't talked about is conductance. Right? Now, conductance is the inverse of resistance. So, and the unit of conductance is a unit called Siemens. So the G1 and G2 and G4, they're resistors, but their values are given in conductance rather than in resistance. So let's have a look at that. Excuse me. So we have to find the total current Ix, and if we had all the resistor values in ohms, it'd be trivial, right? The total equivalent resistance would just be R1 plus, I'm going to call it R2 plus R3 plus R4. The tricky part now is that two of our resistors are given as conductance values. And as I said, the conductance is just the inverse of resistance. So the way to write this one down to find the total equivalent resistance is just R1, which we have, plus 1 on G2, which converts our Siemens into ohms, to R3, and then we just add 1 on G4. Right, so R1 was 8 ohms, 1 on G2 is going to be 2 ohms, R3 is just 2 ohms, and 1 on G4 is just 5 ohms. So our total is equivalent resistance is 17 ohms, but that's not what we're after. What we're after is the current. So I equals V on R, and here our V is 12 volts, and I'll just let's try that again. Right, so our I equals V on R, voltage is 12, resistance is 17. So let's have a look at what 12 on 17 is. So there we go. And if you were doing this to 4 significant figures, I'd go 0.7059, right, which is what I think I did before. Try to do everything. Answers are probably okay in 3 significant figures, but all your intermediate results should be to 4 significant figures. Okay, that looks good. Okay. Problem 5. All right, this one is about power and about voltage dividers. Right, so let's take a picture. Let's just see what's happening there. Okay, I really wish OneNote would get its act together. So let's go down here and insert that screenshot. Okay, so we have VS, we have R1, we have R2. So the first thing we've got to do is figure out what the current is, right? And we know V equals IR. We can see that R1 and R2 are in series because they share uniquely a common node. So that means the total equivalent resistance is 51 kilo ohms plus 68 kilo ohms. What's that? 119 kilo ohms. So it's 51 plus 68 kilo ohms. And that is 110 plus 9, so 119 kilo ohms. So that means our current is V on R, so 24 on 119 by 10 to the 3. Let's see what that gives us. And it's, excuse me, I'm just going to quit OneNote completely and start it up again. See if that helps. Okay, sorry about that. So equivalent is, let's go with blue. 51 kilo ohms plus 68 kilo ohms, which is a total of 119 kilo ohms. So our current is V on R, which is 24 volts divided by 119 by 10 to the 3. Let's see what that does. So 24 volts divided by 119 by 10 to the 3. And that is, I would tend to call that 201.7 microamps. Okay, so it's going to be equal to 201.7 microamps, right? So this is the Greek letter mu, sometimes called mi, but and it represents by 10 to the minus 6. Okay, there's our current, and now we can figure out what VR1 and VR2 is. VR1 is just I times R1, which is 51 by 10 to the 3, and VR2 is just I times R2, which is 68 by 10 to the 3. Right, and let's see what that gives us. So 51 by 10 to the 3. I'm just going to copy that so I can, so multiplied by 51,000. So that's 10.29. And 68 by 10 to the 3 gives us 13.71. And it looks like that's what I got before. And then how much power is dissipated in each resistor? We could just multiply the voltages by the currents. So let's do that. Right, so PR1 is equal to I times VR1, which is equal to 201.7 by 10 to the minus 6 times 10.29, and PR2P, it's so PR2 is equal to VR2, I times VR2, which is again 201.7 by 10 to the minus 6, and this time times 13.71. Let's see what they are. So our current times 13.71 is 2.765 milliwatts. Or I suppose this just asks for watts. So 2.764. It's interesting. I got 2.765 in my calculation here because I was only using right. So that one there is 0.002765 watts, and this one, let's see if we can get it, 10.29. Right, it's 0.002075. And the only slight discrepancy between what I'm doing, what I've written and what I typed in previously is that last significant figure is out a bit. What I'll do when we get back to the web work, I'll change the numbers to 5 and, well, both of them to 5 and see whether that changes, whether the answer is correct. I suspect it's still okay. And then how much power is dissipated by Vs? Well, current is 201.7, the voltage is 24. We just multiply those two to get, right? So the PVS is 24 times I, and let's see what that comes up to in our calculation. Right, 0.004840, which is what I had before. And notice it's dissipated, right? So this is going to have to be a minus, because batteries don't dissipate power, they provide power, right? So it's minus 0.004840. And the units are watts. And one problem with this last question, right? Write an expression. You nearly always want to think about power going in one direction all the time, and that some of the powers will be negative, right? So in this case, you're just assuming that everything is dissipating power, and the sum of those powers has to be 0, right? So PVS plus PR1 plus PR2 equals 0. When WebWork tells you to use particular variables, make sure you use those variables. It'll give you an error if you don't. Okay, so let's just go back and see what happens if I think my numbers this time round were 5 and 5, and let's just submit the answers and see if it yeah, it still gives me them as being correct. There is a bit of wiggle room in these answers, but try and be as precise as possible. Like I said, usually 3 significant figures is fine for your final answer. Okay, that was problem 5. I'm just going to take a quick break for a while. Let's make it about 10 minutes, and I'm going to stop recording the video and I'll start it again